This presentation is delivered by the Stanford Center for Professional Development.
So we've seen vector, grid, stack, and queue, which is what we were doing on Friday. And these form the group we call the sequential containers, where they're storing and retrieving things on the basis of sequence. You place things LIFO into the stack, last in, first out, right? You put things in the vector by index, right? Retrieve by index, right? There's a sequence, right, that's being maintained behind the scenes to store and retrieve the data. All of these containers have the property that they don't really examine your elements, they just store them. So you can put things into a stack, but it never really looks at them. It never looks at the strings you put in or the students that you put in the vector. It just holds on to it, and then when asked to give you something back by an NQ, a DQ operation or a get-at or something like that, it retrieves what you earlier placed there. These are not very fancy, right? They do things that are very useful, but the bang for the buck is, mostly in terms of just modeling a particular behavior like the stack and the queue, and then allowing you to kind of use it easily without error. The associative containers, which is what map and set belong to, are the ones where you're really getting a lot of power out of them, where they do something that actually is hard or inconvenient or inefficient for you to do manually. They're not about sequencing, right? They're about relationships. And so the set is a little bit like a vector in the sense that it's a collection of things without duplication, but has fast operations for checking membership, adding things, removing things, checking to see if something's in the set in a way that the vector, right, you'd end up kind of trudging through it to see, well, do I already have this value in here? There's no easy way to do that with the vector as it stands. And so set gives you this kind of fast access for, is this in the set, is it not? As well as a bunch of operations allow you to do high-level combinations, like take this set and union it with another, or intersect it, or subtract this one from that, and get the mathematical properties of sets expressed in code. The map, even fancier in some sense, is a key-value pairing that you want to be able to do some kind of lookup by key. I want to have a license plate number, and I want to know what car that's assigned to and what its make and model and owner is. The map is exactly the thing you want for that, where you have some sort of key, some sort of tag or identifying ID that you want to associate some larger thing with, or some other thing with for that matter, and be able to look that up and make that pairing and retrieve that pairing information quickly. Both of these are designed for very efficient access. It's going to be possible to do these lookups and additions and combinations in much faster than you would be able to do if you were doing it manually. We're going to peek under the hood in a couple weeks and see how that implementation works out and why. But for now, what's pretty cool as a client is you just get to do neat things with it. Stick stuff into it, check things, build things on top of it, taking advantage of all the power that's there through the kind of simple interface without having to learn what the crazy internals behind it are is not something we have to worry about in the first pass. So we'll talk about map. As I said, it's a collection of key value pairs, sort of modeling a dictionary, right? A word and its definition. It could be that it's the student ID and it's their transcript. It could be that it's an index, which tells you what a word and what pages it appears in this text. So there's a key, there's a value. You have operations that once you create a map where you can add a new pair, so you add a key and a value together and stick them in there. If you attempt to add a different value for an existing key, it will actually overwrite. So at any given time, there's exactly one value associated with per key. You can access the elements that you stored earlier, saying, I've got a key, give me the associated value. I can check to see whether a key is contained in the map, just if I want to know, is there some entry already there? And a couple of the fancy features we'll get to in a second, it has some shorthand operators and some access that allow you browsing. So some examples of things that maps are really good for. So map turns out to be just ubiquitous across computer science problem solving. You probably saw the hash map, right, in your 106A class, right? And you got a little bit of work out of that toward the end of the quarter. This guy, there's just 1,000 uses, right, for which a map is a great tool. So a dictionary is an obvious one, right? A thesaurus, right, where you have a word mapped to its synonyms. The DMV, right, which has license plate tags that tell you the 3 cars I've owned in my life and what their license plate numbers were. Any sort of thing that looks like that fits in the maps goal. So let's take a look at what the interface actually looks like. This is a little bit simplified. I removed a couple of the advanced features I'm going to get to in a second. The class name is map, It's templatized on the value type. If you look at the add operation, it takes a string type for the key and a value type for the value, and that means that the map is templatized on only one of the half of the pair. That the pair is always a key, which is a string, mapped to some other thing, whether it's a student structure or a vector of synonyms or a string which represents the definition, right? That value type can vary based on what the client chooses to fill in the template parameter with, but the keys are always strings. I'll kind of get to why that is a little bit later, but just to note it while we're here. So things like remove and contains key and get value that all operate on a key always take a string, and then what they return or access is templatized by this value type. So there's one little thing to need to know a little about how the interface works, right? When you create a map, it is empty, it has no pairs. If you ask it for the size, it tells you the number of pairs in it. If you ever add something to a key that was already present, so if earlier I'd said Julie's phone number is this, and then I later went in and tried to add under Julie another phone number, it will replace. So there will not be two entries for Julie, right? There's always exactly one. So add sometimes is incrementing the size, and other times, right, the size will be unchanged, but we'll have overwritten some previous pair. Remove, if there was a matching value, we'll decrement the size. If actually there wasn't a matching entry, it makes no changes. Contains key can tell you whether something's in there. And then get value has a little bit of a quirk in its interface that you'll need to be aware of. If you ask it to retrieve a key that doesn't exist, right, it's got a little bit of a problem there. If you say, give me the phone number for Julie, it's supposed to return to you the previously associated value, something of value type. Well, if you ask it to get a value for something and there was no pair that matched that, it has a little bit of a conundrum about what to return, right? If, for example, if this table were storing, numbers, maybe we're storing the, latitude and longitude of a city. Well, if you asked it to return, the value for a city it doesn't know about, what is it supposed to return? Like, what is the default, some sort of sentinel value that says no latitude, no longitude, right? It's like, well, what is that, right? If you were getting strings, if you had definitions, you might return the empty string, right? If you were returning numbers, it might be that what you want to return was 0 or -1. There is not for all types of values, right, some clear identifiable sentinel that would be appropriate to return. So what happens actually in get value is if you ask it to retrieve a value for something that doesn't exist, it throws an error, right? There is no other sensible return value it knows of, and so it treats it actually as a drastic situation. That means that if you are probing the table for something that you traditionally want to be checking contains key if you're not positive that it's already in there. If you do know, it's fine to go ahead and get value through, but if you are querying it, it's a two-step process to verify it's there before you go get it. So I got a little bit of code. I'm going to go actually just type this code rather than show it to you pre-written, because I think it's easier to learn something from when I actually type it. So I'm going to go ahead and just show you. So what I have here is a little bit of code I wrote before you got here, which is just designed to take a particular input text file and break it apart using stream extraction into words, right? In this case, tokens that are separated by white space using the default stream extraction. So it has a while true loop, right, that keeps reading until it fails. And then in this case, it just prints them back out. What I'm going to do is I'm actually going to gather those words and I'm going to put them into a map. So this will be my plan. So let's build a map that's going to map words to counts. So the number of times a word occurs in the document, right, will be stored under that key. So the first time I see the, I'll put a 1 in. The next time I see a the, I'll update that 1 to a 2. And so on. And when I'm done, I should have a complete table of all the words that occurred in the document with the counts of the number of times they occurred. So let me go ahead and I'm going to pass it up here by reference so I can fill it in with something. And then what I'm going to do here is I'm going to say if m contains key word. So this means that there was an existing entry. I'm going to add to it under the word okay, let's take a look at what we did here. If it was already there, then I'm going to get the value that was previously stored underneath it, add 1 to it, and then stick it back into the table. So that add is going to overwrite the previous value. If it was 4, it's going to retrieve the 4, add 1 to it, and then overwrite it with a 5. In the case where it didn't contain that key, so there has no occurrence of this has been seen yet, right? We go ahead and establish a new entry in the table using m.add of the word with the count 1.
Question?
Yeah.
If you try the remove member function and there's no value there, does it also throw an error?
It does not, actually. So remove can actually, probably it has to do with a little bit about, well, can you do something reasonable in that case? And remove in this case can say, well, there's nothing to remove, right? Get value just can't do anything reasonable. It's supposed to return you something, right? And it's like, well, there's nothing to return. I can't make it up. And that's why that's considered a more drastic situation. Question?
You passed the map on the wrong line.
The map on the wrong line. Oh, yeah, you're right. I totally did. Thank you very much. That was going to give me quite an error when I got there. There we go. Let's fix that. Okay, thank you very much. And so then maybe when I'm done, I could say num unique words and then m.size. So if we let this guy go, it's going to complain all over the place because it says, what's this map of which you speak? And I will tell it, here's a header file you'd like to hear. Okay, so there were 512 unique words in this document. You know, just it's the text of some handout we had earlier that I just took and put in a text file. So this shows kind of the basic usage pattern, right? Will typically be, oh, I'm sticking stuff in there and then potentially updating and changing, right? And then I, in this case, was using a count at the end. I'm going to note one funky little thing about the map while I'm here, because map has a shorthand access that allows you to retrieve the value associated with a key using a syntax that looks a little bit bizarre, but it's kind of becoming common, is to, instead of saying m.getValue word, that you say m of square brackets of word. So that looks a little bit like an array access, and the first time I saw this, I have to say I was just shocked, and I thought, oh my God, what an abuse of the notational system, but it has become so ubiquitous in sort of languages now that I actually don't consider it so frightening anymore. It's basically saying, like, reach into the table, and instead of using an index to identify which element you're doing, you're using a key, and it's saying, reach into the bucket that's tagged with this index and get the value back out. So this is effectively an m.getValue of word, but using this syntax. There's something, though, that's a little bit wacky about this syntax, though, is it's not exactly equivalent to get value in that it doesn't mind if you try to access something that doesn't exist. And what it will do is its strategy is if you access a word, m of subword, where this is not an existing key, it will create a pair. It will tag it with the key you asked for, and then it will kind of leave the associated value as to whatever the default value for that type is. So in this case, it's almost like you just declared an int variable on the stack. What do you get? Turns out you'll get garbage, right? You'll get kind of an uninitialized number, which is of very little value. But the side effect of then having set this pair up was that then we could immediately go in and write on top of it and make the assignment into the 1. And so whatever junk contents were there were only temporary, and then I immediately overwrote it with that. And in effect, that also means I can do things like this, right? Where I do m word plus equals 1. And now I'm using it kind of both for the add and the get value part. So the m bracket form kind of handles both the things you think of as being add, adding something into there, overwriting or adding a new value, as well as just retrieving it, right, when you want to read it like a get value. So you'll see both of these used, right, but they do have a little bit of a quirky behavior that's different, that using the get value right without an existing key, right, throws an error. Using it this way actually kind of sets up an empty error that the assumption is that you're using it in this context where you're trying to immediately create it and overwrite it. Question?
Does the case not matter for maps? Meaning, does it, if it's...
So case does matter. So if I had the word, capital T, the, and lowercase the, those are different words. So it really does, basically what you think of as string equals, right, comparisons at the base level. If I wanted it to be case insensitive, then I would need to actually go out of my way to convert the keys to uniform case to guarantee that they would match other forms of the word. Okay. So let me go back and that's a little bit of code there. So let me just review a little bit about where we're at, right? That the shorthand operator that we have. I said I would explain, well, why is it the keys, right, have to be string type? that if we're trying really hard to build these general purpose containers, it seems like it'd be extra convenient if actually we could say, well, the key is an integer and the mapping is, maybe these are numbers, student ID numbers, and it's a student's record that's there. Why does it have to be string type? Well, it turns out, right, that it really does use the known structure of strings to store them efficiently. So it's capitalizing on certain properties that strings and strings only have to decide how to store those things so that it can actually do this very fast lookup that does not generally apply to other types of things. That I couldn't say the key is a student structure and you have to match student structures. It's like there's not easy, efficient ways to match any kind of value type, but there are certain things you can do with strings and strings only that it's capitalizing on. So in the case where you have something you're trying to use a key that isn't already in a string type, the kind of recommended way to get around that is, well, you have to figure out a way to convert it to a string. So if you have an int, the student ID number that you want to use, or a phone number, something like that, well, you just convert it into string form. So you take the integer, you make it into a string. You take if you have like a first name and a last name and you want to use them both, well, then you concatenate them together and use that string as the key. Just ways of building a string out of what you have. It's a little bit of a hack, but solves the problem without too much trouble in most situations. The other question that comes up is, well, what if I have more than one value for a key? The thesaurus example I gave earlier. The key is the word. The thing I want to map it to is the synonyms, that list of the words. If I did add of word with its synonym, right, each subsequent synonym would just replace any previous pairing I'd put in, right? If what I really want is a one-to-many relationship, one word, many options, then what I can do is just use vector as the value. So build a map containing vectors containing strings. So I'll get a nested template out of that. And then when I want to add a new synonym to the map, it's a matter of pulling out the existing map that's there and adding it to the end of that vector. So it actually is kind of a two-step add to get it into the vector and get that vector into the table. So the last thing that's missing is one that I'll go back to my code and we can do together, is once I've put the information in the table, I hope you believe me that I can get it back fast. I can check to see if there's an existing entry and do the lookup by key, put new entries in, replace it, overwrite, all of that, right, in the interface so far seems just fine. But let's say I just wanted to see that whole table. I want to print my class list. I want to see the thesaurus or the dictionary just spewed out, or just actually walk through it and look for new words. As it stands, right, the interface doesn't give you that access, right? They're not indexed, right? They're not in there under slot 0, slot 1, or slot 2. It's not like a stack or a queue where you can just dequeue them back out to see all the things you put in there. They kind of go in, and so far it's the Roach Motel. You can put them in, and if you know who you're looking for, you can get them back, but there's no way to kind of scan the contents. What we're going to see is that map provides access to all the elements using a tool called an iterator. This is the same tool that Java uses, so if you've seen that, you're already ahead of the game, where you would like to see the entries that are in there. Rather than giving you a whole vector or some other kind of random access version of it, it provides you with the little intermediary. In this case, this class is called Iterator. You create an iterator on the class. Here, let me just go write the code. It's better to see that. So if I got here and I said I want to see what they are, that what I do is I create an iterator. The map's iterator name is a little bit wacky. So there are iterators on both the map and the set, and to distinguish them, because they're similar but not exactly the same thing, the iterator type is actually declared within the map class itself. So it's actually map of the type in angle brackets, : iterator is the name of the iterator for an iterator that walks over a map containing integers. We get one of those from the map by asking for it with the iterator member function. So that sets you up an iterator that's positioned to kind of work its way through it. The map iterator makes no guarantee about what order it will visit them in, but it will visit them all. It uses a syntax that looks like this. And I say iter.hasNext. Are there more things to retrieve? So the iterator is kind of keeping track of where we are as we're working our way through the map. If there are more keys we haven't yet visited, haven't yet retrieved from the iterator, it will return true, in which case the call to iter.next will retrieve the next key to be visited and then advance the iter. So it will have moved past that and kind of moved that to the already visited side, and now it'll continue to work on the things that are unvisited. So as I keep doing that, right, iter.next is both retrieving it and advancing it. So you typically want to call that once inside the loop to get the value, and then check that has next again to see whether there's more and keep going. It gives you just the key. It doesn't give you the pair. The pair is just an easy call away, though. So I can say key equals, and then m of key. And so using the shorthand syntax or the get value, right? Either way, once I have a key, it's very easy to look at the value. In fact, it's so efficient, it means there's actually really no harm in just getting the key and going back in to get the value separately. It still works out just fine. So when I do this, this should actually iterate through, show me every entry in the vector or in the map and the count for it. And so one thing I will note is that the sequence by which it's traveling through seems to be effectively random. You see my reasonable experience few following somewhere using the numbers 1, 4, 2, So there is no pattern, there's no rhyme or reason. It turns out it is actually internally doing something kind of sensible, but it does not guarantee, as for the iterator, anything predictable to you about which sequence it will visit them in. It says, I will get them all before it's all done and said, but don't count on seeing them in alphabetical order, reverse alphabetical order, or in order of increasing value or anything clever like that. It will get to them all. That's all you can be sure of. So that is the same code that's up here. Question?
So on the previous page, the previous slide, you mentioned something about synonyms. Finding the word with the largest number of synonyms, you would have to use a vector for that?
Yeah, so if I had, a one-to-many in that case, and maybe it was synonym to vector of strings, right, then I could use the iterator to go through and say, well, how big is this vector compared to the other vectors I've seen so far? So I'd keep track of, let's say, the max so far. So you'd run an iterator that, like, for example, let's just say I wanted to find the most frequent word. That's about the same operation. Let me come back over here. If I just want to see the most frequent, I could do this. I could say string max, right? And I'll say int max count equals 0. So the max is empty here. When I get this thing, I say if m of key is greater than my max count, then I want my max to be the key and my max count to be m of the key. So I've started right with no assumptions about what the max is, right? And anytime I see something that's greater than the max I have so far, I update that. And so if this were a vector, I would be checking to see that the size of the value was bigger than the size of the previous vector. When I'm done, I can say max equals max count. And so it turns out the most common word in there, what a surprise, right? It shows up 42 times. The same sort of access right would be used, if there was some other thing I want to do. So what the iterator is just giving us is a general purpose way of walking through all the values. And then what you want to do with them when you get there, is your business. You want to print them, you want to put them in a file, you want to compare them to find the top two or the smallest or the biggest or the whatever is, up to you. So it's just giving you access to that data that you stuck in there and get it back out.
What is iter.next?
So iter.next is, think of it as an abstraction, right? The idea is that it's almost like it's got a little pointer, right? And it's kind of just, like if I were in charge of kind of walking through this class and returning each student, right? It is a pointer that given a certain student will return you the student I'm currently, pointing at, right? And then move to another random student, right? And at any given point when I've done them all, right, that has next returns false. And so next does two things, right? Which is return to you the key that you haven't yet seen, but advances kind of the iterators as a side effect so that you can now test for, are there any more? And if so, the next call will return a different one. So every time you call, it returns a new unvisited key in the map until they're all gone.
Does it return the current key value or the next one?
Well, it returns the next one in the iteration. So it's almost like you can imagine that it's almost like a caret that's between characters at any given point, right? It will return the next character, but if you call it again, it will return a new one. So it never returns the same value unless there was the same thing being iterated over. So it advances and returns in one step. That is key. There are some iterators that don't have that design. They tend to return the current one and then use side effect, right? The STL iterators, for example. And this one is kind of more of a Java-style iterator. It does both. So if you needed to use the value a couple times in there, you'd probably store it in a local variable and then use it throughout that thing, and then only call iter.next once in each loop. Okay. There is an alternate way of doing something to every pair in a map. I'm actually just not going to show it to you because I think actually it's in some sense overkill. So there is something you can read about in handout 14 and look at, which is called the mapping function. I'm going to actually just skip it because I think it actually just it confuses the issue more than it helps. When you know how to do iteration, it's a great way to get access to all things in a map. And since the other function actually I think is just a more complicated way to get at the same functionality, I won't bore you with it. So then let me tell you about set. And once you have set, you've got it all. So map, I think, is the heavy lifter of the class library. The set is kind of a close second best in terms of just everyday utility value. What a set is a little bit like a vector in some ways, but it has the added features that there is no sequencing implied or maintained by it. If you have the set that you've added 3 and 5 to, if you add 5 and 3 in the other order, you end up with the same set when you're done. Those two sets are equal, they have the same content. So it doesn't consider the order of insertion as important at all. It's just about membership. Does it contain these values? There are never any duplicate elements. If you have a set containing 3 and 5 and you attempt to add 3 again, you don't get the set 3, 3, 5, you just get 3, 5. So kind of like the mathematical property that it derives its name from, right? There is just existence. You know, is the member in or not? And adding it again does not change its status if it was already there. So your typical usage is you make an empty set. You can use add, remove, and contain. Stop right on individual elements. Add this one, remove that one. Contains. Remove has the same behavior that it did on the map, which is it kind of silently fails if you ask it to remove something that wasn't there. If you ask add to add something that was already there, it silently doesn't change anything. So both of those operations just kind of quietly deal with cases that might be a little bit unusual. And then contains will give you information about does this member exist in the set. All of those are very efficient. Can be done many, many, many times a microsecond without taking any processor time at all. So that means it's very handy for like throwing things into a set and then later wanting to know if it's there, as opposed to walking your way through a vector piecemeal to see if something was there. So for example, vector doesn't have anything like this. If you want to know if Julie is in your list of students and you have them in a vector, right, the only way to know is to walk through it sub 1, sub 2, sub 3, until you find it or you run out of entries to check. The contains operation does a blinding fast sort of check and can almost immediately tell you is Julie in there or not, whether your entries are 1,000, 1,000,000, a billion. Pretty much immediate access to dig it out. It also offers these high-level operations. And these actually are where sets are particularly valuable, is this idea of unioning, intersecting, subtracting, checking to see whether two sets are equal, so they have all the same members, or whether one is a subset of another, that allow you to model, a lot of times the thing you're trying to take your code to do is something that in the real world needs a subset or an intersect kind of operation, right? You'd like to know if the courses you have taken meet the requirements you need to graduate, right? Well, if the requirements to graduate are a subset of what you take, whether they're a proper subset or not, if they're all in there, right, then you can graduate. If you want to know if you and I, right, are taking any classes together or have any requirements left that we both need to do, we can take the requirements, subtract what we have, see what's left, intersect that, right, to find out what we have left to see if there's any classes we could take together and both satisfy requirements. Any kind of compound Boolean queries, like when you're trying to do searches on an index, you want to see pages that have this word or that word and not that word, are very easily modeled in terms of sets. If you have this set that have A and the set that have B, if you intersect them, it will tell you about which things have both. If you want to see the or, you can use the union and find out which things have either. Sometimes you just use sets simply for this idea of coalescing duplicates. If I just wanted to see the set of words that were in my file, and I don't care about how many times the word occurs, right, I could just dump them all into a set, and then when I'm done, I will know what the 512 unique words are, and I will have not had to chase down, did I already have a copy of that word, because the set's add just automatically coalesces with any existing entry that matches. So let me show you its interface. This is probably the biggest of all our classes in terms of number of member functions there and features of them. I'm not going to talk about the constructor just yet because it has something scary in it, right, that we're going to come back to, which is a little bit fancy in terms of how it works. But there's a default argument over there, just so I'll note that. So that means that actually if you don't specify, in some situations the set doesn't need that argument and can kind of figure out for itself what to do. So we can create a set, right? We can ask for the size is empty, just checking to see if the size is 0. The things that operate on a single element here, adding, removing, containing. And then ones that operate on the set as a whole, comparing it to another set. That set there is one of the few places where you're allowed to use the name set without the qualification. That's because we're in the template. And in this situation, this set without qualification is assumed to be whatever set is currently being built. So if I have a set of int, the equals method for set of int expects another set of int as the argument. Same for is subset and union and intersect. So it actually kind of matches it out correctly all the way through so that you can only union sets of integers with other sets of integers. That should make sense to you. And these operations, right, return the Boolean, these guys actually destructively modify the receiver. So you have a set that you're messaging with the union with, you give it another set, it will join it into the receiver sets. The receiver set will be enlarged by whatever new members are contributed by the other set. Intersect could potentially shrink this set down to just those elements that are in common with this other one, and then subtract takes all the elements that are in there that are present in here and removes them. So you can think of those as just modeling what the mathematical formulation for those operations are. It also uses an iterator. Like the map, once you stick them in there, right, they're not indexed, they're not by number, there's no way to say give me the nth element, they're not, there's no sequencing to them, so you use an iterator if you want to walk through a set and see what's in there. So let me write you a little set code. Any questions about its basic interface? Yeah.
Why would somebody use a vector over a set?
So sometimes you actually do care about ordering, right? Or you do want duplicates, right? You might have, a bunch of names where maybe some people are going to have the same names. Or the ordering really is that you want to know who's in what room in a dorm. You might be using the index to say it's in room 100, that's at what's indexed. So definitely where you care about that index, right? And where you also want that random access. That I know a particular number and I want to see what's in that box, there really isn't that same feature in a set. Like there's no way to get you the nth member. Or so if you just wanted to pick a random member out of a set, right, the only way to do it would be to open up the iterator and take a random number of steps forward, right? Whereas in a vector, you can say, well, just pick from 0 to n-1. So there are definitely things that vector can do that set doesn't. And it just depends on the task to which you have. Do you need duplicates? Right? You're definitely stuck with vector. Do you care about that random access? Do you use the index in some interesting way? Do you care about recording the sequence, like knowing who was first or last that you added? Set doesn't track those things in the same way. So let me write a little code that uses a set. And let's write this. I'm going to write something that tests the random number iterator. Every time I do this, it alarms me. But I think it's good to know. I'm going to keep a list of the numbers I've seen. And I'm going to write a for loop that then, I don't know, let's just run it till we see a duplicate. Okay. I'm going to generate a number between 1 and 100. If scene.contains that number, then I'm going to break. But let me do a count. No, that'll be fine. Actually, that'll be fine. Otherwise, I'm going to add it. And then I'm going to print found scene.size before repeat. So what you might be hoping, right, is that if a random number generator was truly random and but still a little bit predictable in this case, if I asked it for the numbers between 1 and 100, you'd like to think it would take about 100 iterations before it would get back to a number it's seen. But certainly, right, given it's random, it's not actually picking and choosing and without replacement, but it's just kind of bopping around in the space 1 to 100, and it may very well light back on a number it's already seen before it would get around to some of the other numbers. So when you run this, you're kind of curious to see, well, what is it like? Let's find out. Every time I do this, I always think, wow, the random number generator really not that random. But we'll see what today says. So I'm including random to get access to random integer. And I'm going to my set here. And then I'm going to add one called randomize here at the top. Right, that initialize the library, right, so that we have a new random sequence for this particular run, which will allow us to have different results from run to run. It said 23 numbers before repeat. Okay, what if I run it again? 7 before repeat. Let's try it again. 20 before repeat. So showing you a little bit about that. 7 again. 6. Okay, 10. Like, is it ever going to get close to 100? No. So it just tells you that it pops around, but it actually does not. It is pseudo-random, which is one of the words that computer scientists use to say, yeah, don't count on it being really random. I would not run around my casino on the basis of numbers being generated by your average C++ random library. But there you go. So in this case, just using it for containment, right? So that each time through, right, I can add that new number and then check the contains. Both those operations operating very quickly. If I did this instead with a vector, right, I could accomplish the same thing, but it'd just be more manual, right? I'd stick it on the end, and then if I wanted to see if it was there, contains is not an operation vector support, so I'd have to walk through the vector from 0 to the length minus 1 and try to do the matching myself, right? Which gets slower and slower as the vector gets longer, right? And it's just a hassle to write that code, so having contains around saved us a little bit. If I want to print my set, so why don't I go ahead and just at the bottom show that the iterator gets used on the set. Has the similar kind of formed name as the map. So the iterator, in this case capital I, is a nested class declared within the set. I ask the set to give me its iterator while there are things left to pull out. Then I will pull out it and print it. And so there's the sequence, let's say, of 20 or so numbers. So this highlights something that's a little bit distinctive about the iterator as it applies to the set, is that those numbers, 15, 16, 22, 24, 37, are coming out in increasing order, all the way down to the bottom. And if I run it again, I will get the same effect, but perhaps on a shorter list, right? That the set's iterator is not as unpredictable as the map iterator was. That the set iterator, that in fact, part of how the set is able to supply its operation so efficiently is that internally it is using some notion of sorting. That it is keeping track of kind of things by ordering. In this case, the increasing order is the default strategy for how it lines things up, and that the iterator takes advantage of that. Since it is internally storing it in sorted order, it might as well just use the iterator to walk them in sorted order. And that tends to be convenient for somebody who wants to process the set. So as a result, you can count on that, right? That when you're using a set, that the iterator will pull out the values from kind of smallest to largest. So for example, for strings, it would be the lexicographic ordering, that kind of slightly alphabetical thing based on ASCII codes, that it would produce them in numbers. They'll go from smallest to largest as a convenience, and it happens to be kind of nice for just browsing it in alphabetical order is often something that's handy to be able to do. Okay. You head back over here. And so, code we just wrote, right, printing the set, right, doing the random test. I can apparently reproduce my own code on demand. And then here shows a little bit of some of the fancier features you can start doing once you have kind of sets in play. So if I were keeping track of, for the friends that I know, right, who they consider to be their friends and who they consider to be their enemies. Of course, those are very small lists, I'm sure, for you indeed. But if I were putting together a party, what I might want to do is say, well, let's invite everybody you're friends with and everybody I'm friends with, but then let's make sure we don't invite anybody that one of us doesn't like, right, that's on our enemy list, right? And so by starting with a copy of the friends that one has, unioning that with the two's friends, right now I've got the enlarged set, which includes, and so note that I did a set string result equals one friends. That actually does a complete deep copy. So the map and the set, just like our other containers, know how to copy themselves and produce new things. So I got a new set that was initialized to the contents of one's friends. I took that set and destructively modified it to add two's friends. So now the result has an enlarged circle of that. And then I'm further destructively modifying it to remove anyone who was on my enemy list and your enemy list to get us down to kind of that happy set of folks that we both like, or either of us likes and neither of us dislikes, to do that. And so things that you can imagine if you had to do this with vectors, right, would start to get pretty ugly, right? Walking down your list and my list to see who's matching, to see who you have, I don't, right? To make sure that everybody got one and only one invitation, right? The set is automatically handing all the coalescing of duplicates for us, and then allowing you this kind of high-level expression of your actions is very powerful, right? That if in the end what you're trying to model is this kind of rearrangement, then being able to say union, subtract, intersect really helps the clarity of your code. Somebody can just read it and say, oh, I see what they're doing here, right? Doing set operations to get to where we want to be. Question?
What if one and two have the same enemies, and so when you subtract one's enemies, and then you try to subtract it again with two, and it's not there?
Yeah, so it turns out subtract will say remove these things if they're present. So if you and I have some of the same enemies, after I've removed them from your list, I'll remove them again from my list. Well, it turns out they won't be there, but it doesn't complain. So like the remove operation, if you ask it to subtract some things that aren't there, it doesn't get upset about it. It just skips over them basically. Okay. So set though is a little bit more quirky than the others in one kind of peculiar way. And so I'm going to kind of foreshadow this, and we're going to actually do more serious work on this on Friday, is that the other containers kind of store and retrieve things. They're putting them in buckets or in slabs or boxes and whatever and returning them back to you. But set is actually really has a much more intimate relationship with the data that it's storing. That it really is examining the things that you give it to make sure, for example, that any existing copy, right, is coalesced with this one, that when you ask it to go find something, it has to do some kind of matching operation to say, well, do I have something that looks like this? It's doing this sorting, as I said. Internally, it's keeping them ordered. Well, it needs to know something about how to do that ordering, what it means for two elements to be the same, what it means for one element to precede another or follow another in some ordering. Okay, but set is written as a template. Right, set takes any kind of elem type thing. How is it you compare two things generically? That actually is not an easy problem, right? I'll show you a little bit about this code, and then we'll talk about this on Friday more, is that one way you could do it is you could assume that, well, if I take the two elements, I could just use equals equals and less than. If I just plug them into the built-in operators and say, tell me, are they equal? What does equal equal say? Is one of them less than the other? Tell me that, right? Using the built-in operators will work for some types of things you would store. It'll work for ints, it'll work for doubles, it'll work for characters. So all the primitive types, right, have relational operator behavior. Even things like string, which is a sort of fancier type, also has behavior for equals, equals, and less than. But you start throwing things like student structures into a set, and I say, take two students and say if they're equal, equal, we're going to run into some trouble. So I'll show you that error message, and we'll talk more about what we can do about it when I see you again on Friday. If you have something you need to talk to me about, now would be a good time before I run away. So if you wanted to see me today in office hours.